I'm sorry, I was planning to be there in presence, but due to personal reason, I couldn't come. So,
Okay, we remind the code of conduct based on the shared values as kindness, trust, respect, diversity, inclusiveness. Any kind of bullying, harassment, and aggression are never permitted and should be reported directly or by email to the two OMSBAD persons, Apragita and Dominique. We remind to check on name tags for the stickers indicating the contact comfort level and to use masks indoors. For any local and logistic
let's start by first reminding you.
I cannot hear you anymore. I don't know if you're muted, perhaps.
Of Gaia for the first 5 years of nominal mission that actually ended at the end.
Isabella,
Sì.
you can share your presentation.
Io sento, I hear in background another presentation by somebody else, but probably in another room.
Yes.
And, this is fine, I guess. I don't know. Okay. By the way.
After 5 years,
I will share my presentation.
Yes.
On average, 70 measurements.
Thank you.
In the GDP and GRP.
Okay, here we are.
RBS measurements.
Can you see it?
In all the regions of the scanner, Gaia scanning low, the number of locations is much larger.
Yes.
Can you see it?
Yes. Yes.
Okay.
Now with the survey that.
All right. Okay. So I hear this background voice, which is a bit annoying, but I will survive, I guess. So first of all, I would like to thank the organizers for inviting me to give this talk and also to help with the organization of this session. I'm really sorry I cannot be there in person with you, but unfortunately I had to cancel at the very last moment. And if you can hear my voice, probably you understand also why. By the way, in my talk, I will first give a brief overview of the SKA Observatory and of its broad scientific goals. And then I will illustrate a number of science cases where the SKA and the LSST present clear synergies. presentation is not intended to provide a complete list of synergies. This is impossible, but just to give a flavor of the many possibilities offered by the SKA and LSST if combined and working together. Before proceeding any further, however, I would like to acknowledge the colleagues that helped me in putting together the synergy slides, which are listed here in this slide. Now, for those who are not familiar with the SKA Observatory is a next generation radio facility which has the ambition to enable transformational science and to become one of the great 21st century observatories that are already operational or will become operational soon on a range of wavelengths. The SKA Observatory is a huge infrastructure, is a gigantic infrastructure, and which is distributed over 3 continents. It will comprise 2 telescope sites in the Southern Hemisphere, and the headquarters are placed in UK, Europe, close to Manchester. Each site will host an array of antennas which will work together as radio interferometers. The first of these 2 sites, of these 2 arrays, the so-called SKA low array, which will be built in Australia and which will operate at low frequencies, as the name says, will operate between 50 and 350 megahertz and will be made of 512 aperture array stations, each hosting 256 antennas and distributed over a maximum baseline of 65 kilometers. The SKA mid array, on the other hand, which will be hosted in South Africa, will operate at higher frequencies between 350 megahertz and 15 gigahertz, and will consist of 196 dishes distributed over a maximum baseline of 150 kilometers. All this, the organization of all this is managed by an intergovernmental organization, or IGO, like CERN and ESO, and there are 24 prospecting countries in the process to join. Among those that are already full members, we have a number of European countries like Italy, Netherlands, Portugal, and the UK, if we want to consider it Europe. Spain and France will also join very soon. The construction of the SKA telescope and infrastructure will cost over 1 billion euros and will be completed in 2029. But right now, we can already use the so-called SKA precursors, which are hosted at the same sites, Meerkat in South Africa and ASCAP and MWA in Australia, which have been built to serve as science and technology demonstrators. Now, coming to a possible synergy with LSST, the first point which is worth to stress here is that the SKA is designed to be a survey instrument. And indeed, its combination of field of view and sensitivity will provide over a factor 100 improvement over existing radio facilities in survey speeds, and this over a wide range of radio frequencies, as shown in this plot here. In addition, the fact that the antennas are distributed on continental scales, together with the fact that we can give a different weight to the many interferometry baselines available, will allow us to map the sky over a large ranges of scales, from arc-minute to milliarsec resolution, which is indeed particularly powerful. Like Rubin, SKA will target the Southern Hemisphere and will follow a tiered strategy with wide area shallower surveys combined with medium deep and deep fields. In addition, LSST and SKA will provide complementary multi-band, multi-epoch, and multi-resolution observations. So together will really provide a full overview of all the possible physical mechanisms happening in sources, in sky sources. So LSST and SKA datasets will really represent a golden mine for joint science exploitation. And this is, in general, independently from the particular science case we are interested to. Another point of which the two experiments have in common is that they both will provide petabyte scale observational data sets, which will be recorded over time. And extracting the signal, the astrophysical information from these data sets will be a considerable challenge. So the two experiments will benefit greatly from sharing expertise, analysis tools, and open sources, numerical codes, for example. Sorry. Coming to science, as far as the SKA is concerned, the science case has evolved a lot along the years. The original SKA concept was based on a very simple but very ambitious goal, which was to uncover the history of the universe through the mapping of the redshifted H1 line over a wide range of scales, well beyond the local universe and up to the epoch of reionization and dark ages. This clearly requires super sensitivity over a wide range of frequencies and spatial resolutions, and this can indeed be achieved only by combining different telescopes optimized to operate at different frequencies. And this explains why we are building two telescopes and not only one. However, it became clear very soon that such an ambitious infrastructure can pursue a much larger suite of science cases. And here is a flavor of the possible science that can be done with the SKA. The scientific science case of the SKA is now very broad and is still evolving very rapidly, driven by the precursor results. As you can see here, a list of the main science drivers, but in fact, the SKA is so versatile that it can be regarded as a multi-purpose infrastructure rather than an experiment with a number of science drivers. So what we can do, we can go from the study of the so-called cosmic dawn and epoch of reionization through the mapping of the redshifted H1 line at the lowest frequencies, as I said, to exoplanetary studies and search for prebiotic molecules at the highest frequencies, passing from galaxy evolution, cosmology, the study of the cosmic magnetism, transients, and so on. This is done through a combination of multiple data sets from radio continuum to polarization to H1 and time domain surveys.
And these are the numbers.
The science drivers from the SKA overlap, obviously, with science drivers from many of the next generation facilities working at other wavelengths, including the LSST, as illustrated here. And synergies are clearly present in all research fields covered by the SKA and LSST whenever a multi-wavelength or a panchromatic approach is critical. An obvious field where synergies between SKA surveys and LSST are huge is the study of the transient universe, and coordinated strategies should be envisaged in this case. Particularly relevant here is the synergy between the high sensitivity and large field of view of the SKA and the high cadence sky monitoring capabilities of the LSST. These capabilities together will allow to make a jump forward in the understanding of the many transient phenomena and of the different physical mechanisms responsible for emission at different wavelengths. Transient studies can involve well-known transient classes like those shown in this figure, gamma ray bursts, supernovae, tidal disruption events, etc. But can also address the more recently discovered and enigmatic class of fast radio burst. Indeed, by combining prompt triggers from the SKA, we coupled with the strong SKA localization capabilities, will allow to investigate the presence of optical emission associated with FRB events, if any, and its properties. And this is particularly relevant case from a radio point of view. In addition, it will be possible to exploit the huge catalogs produced by LSST as well as other surveys like Gaia, Rosita, CTA, etc., to support so-called guided pulsar searches in the radio data of the SKA. A class of pulsars which is particularly interesting to investigate is the class of transitional binaries, which are accreting pulsars observed in both low mass X-ray binary and millisecond radio pulsar phase. And this class is particularly important because they are considered the smoking gun of the so-called recycling scenario, which has been proposed to describe the acceleration of radio pulsars to millisecond period. Combining observations at different wavelengths, in particular optical and high energy, radio, optical and high energy observations and monitoring is essential for a full characterization of these objects. And also very important are polarimetry measurements, as they allow us to determine the magnetic field of the systems and its role in the accretion process. Synergic studies of the Milky Way do not limit to transit sources, of course, and there is plenty of science that can be done in this respect, and I refer to the next two talks for an overview of galactic science and more examples of synergies. Another obvious field of synergy is cosmology, which represents a major driver for both SKA and LSST surveys. This is so true that a chapter in the SKA science book was expressly dedicated to describe such synergies. This chapter is a bit outdated now because it was published in 2015, but the SKA LSST synergy case has been updated in recent more general papers, like, for example, the so-called SKA Cosmology Red Book published in 2018 by Bacon et al. So I refer to these papers for a full overview of such synergies, and I just gave you an example later on. Here, again, a table showing the main cosmological open questions addressed by various major facilities and experiments. As you can see, most of them are highly relevant for both SKA and LSST, which means that both facilities and experiments can measure these parameters and these the cosmological parameters associated with these questions very powerfully. A joint analysis of LSST and SKA can therefore not only provide complementary constraints, but can also help to beat, for example, survey-dependent systematics. An example is shown here. This slide shows the cosmology surveys planned for the SKA, which go from a medium deep survey covering 5,000 square degrees for weak lensing analysis to a wide survey covering the full sky accessible to the SKA, which is about 20,000 square degrees, which is aimed for galaxy clustering and H1 intensity mapping experiments. On the right, you see an example of the benefits of joint LSST-SKA analysis for weak lensing. A cross-correlation of the cosmic shear signal can not only provide better constraints on the cosmological parameters, involved, but more importantly, can help to remove or mitigate systematics, like those, for example, associated to the assumed point spread function shapes at the two wavelengths, in the radio and in the optical. This is clearly shown in the bottom left, in the bottom right figure. Of course, similar exercise can be carried out by cross-correlating radio and optical galaxy clustering, or H1 intensity mapping from the SKA and galaxy clustering from LSST, so through the so-called multi-tracing technique, with the advantage that the full area of the LSST surveys can be exploited in this case. A last clear example of synergy between LSST and SKA is represented by galaxy AGN coevolution studies. Sorry. Only by combining SKA continuum and H1 surveys with the multi-band surveys from LSST, we can really get and gain the fullest picture of galaxy evolution. For example, the radio continuum can provide dust unbiased star formation rates, and H1 surveys can provide the H1 mass of galaxies. Redshifts from H1 can be derived, of course, information on the H1 kinematics in the galaxy, and in particular, hints of AGN feedback of fueling through the tracing of H1 outflows and inflows. On the other hand, LSST can provide photometric redshifts, which are essential for sources for which H1 is not detected, which will be the highest redshift ones, so the most important ones, can provide stellar masses, another estimate of star formation rate, which can be compared to the continuum, radio continuum one, and other parameters based on stellar populations like metallicity, age, and so on. For this science case in particular, very important are the deep fields, of course, to reach the most distant universe. So it is important that the SKA will select its own deep fields, including the LSST deep drilling fields for a full coordination. So concluding, I hope I have convinced you that of the many possibilities that close collaborations between SKA and LSST team can offer. But before getting to the end, I would like to have with you a closer look to the SKA and LSST timeline. As you can see, SKA is a bit behind LSST, with LSST having its first data release between 25 and 29, when the SKA will be only in its early science phase. LSST can therefore count on the full SKA capabilities only from 2029 or 2030, so only from for the last 5 or 6 data releases. However, there is plenty of radio-optical collaboration opportunities already now. As I said, SKA precursors are up and running and are producing already amazing science. And this brings me to the next talk by Grazia, who will give us an overview of the SKA precursors capabilities. Thank you.
The most important thing to take into account in the whole process of managing such a huge amount of data.
Hello. Thanks, Isabella. There is time for some questions.
I would say that something that we are starting to do now.
I can check.
And I strongly recommend to do since the very beginning, LSST, is a cross collaboration with the different.
Giuseppe.
In Gaia, there are different coordination units working with different
I apologize that I arrived a bit late, but I have a curiosity. One of the key issues about the LSST survey across the galactic plane is obviously the wide band and the depth of the wide band along the galactic plane, very, very redneck regions. So I was wondering whether you have already some preliminary ideas or whether you have already checked with what is already available, the kind of opportunities that you can have in this band with the sources that you are going to detect, either with the precursors or with SKA.
What do you mean with wide band? Sorry.
The wide band is the reddest of the 6 bands that LSST is going to use.
Okay.
It's going to from U to Y, and the Y is a sort of a no-body land because it is not near infrared, it's not optical, but is the reddest band that LSST is going to have for improving the quality of the photometry in very highly redneck regions. So I was wondering whether you already have any idea or any specific plan for that.
Well, this is probably a question that can be better addressed by Grazia, who will exactly cover on her talk the science on the galactic plane. So probably she's better addressed than me to answer this question and to answer about possible plans, because I'm sure she and others in the galactic Italian community are thinking about it. I don't know if Grazia can say something, or perhaps this is a question that can be postponed to the end of her talk.
Okay, yes, Giuseppe, I will show some results that actually using radio band, you can look deeper in the very redneck region, and actually we have find new components of different population of the galactic plane. I will show you some results.
So thanks, Isabella. We move on the next talk by Grazia Umana, SKA Precursors, Opportunities for Galactic Science.
La versione 2. Okay, I would like to thank the organizers to invite me. In my talk, I will present some opportunities that the SKA precursor will offer for galactic science. Okay, Isabella showed you already the unique capability of the SKA telescope. But waiting for SKA, we have this what we call precursor pathfinder of SKA, and a series of demonstrator telescope built just to test and develop some technology for SKA to anticipate, as Giuseppe asked, some achievement that SKA will got, and also to, as I say, to be ready for the challenger that we need to face when all the big, huge data for SKA will start to come up. I put a link just to, if you are curious to see what are precursor pathfinder, the difference of them. So one of the precursor of SKA in ASCAP is called precursor because it's in the site when one of the segment of SKA will be built. And you see there is a layout, and you can see what is ASCAP respect to SKA law. Is in Australia. It's around 800 kilometers north of Perth. Just in the slides also recap some capability of SKA law. This is the specification of ASCAP. There are 36 antennas, 12 meters diameters. They have a max baseline of 6 kilometers. It's very important, the concept of baseline, because the baseline of a U interferometer determines the angular resolution that for ASCAP is 10 arc seconds working an L band. What is specific for ASCAP? It has a very new technology for the receivers called PAF. PAF give you, it's a completely different idea respect to the normal receiver that we have for the interferometer. PAF give you an instant field of view of 30 degrees. This means that you have a very, very fast survey speed on this telescope. It is operated by Xyro, and I want to stress you that as the other precursor will see Meerkat, 5 years of this precursor are dedicated to the legacy survey, but when the large survey will start, there will be 10% open to the community. As I say, they have a large survey. They will start next month with ASCAP. To have the high priority, it is EMU, the evolution map of the universe. Wallaby is a survey in H1, and there are other survey in the list. It will take 5 years to complete such survey. And but as soon as the data will be checked by the team, that will be available to the community. At the moment, some data on early signs of this survey available inside, all inside the collaboration. The other SKA precursor is Meerkat, is located in South Africa, and this is a truly precursor, precursor of SKA, because will be the nuclei of SKA. Again, I'll just recap the specific on SKA-mid, the mid-frequency segment of the Scout telescope. You will see where is now Meerkat in white and where it will be SKA-mid. Again, the specification, Meerkat has 64 antennas, a little bigger than ASCAP, and it has a max baseline of 8 kilometers. Again, the baseline will provide you the I don't put here the angular resolution. As ASCAP, Meerkat is working now on large survey, but has also some open call for the community. What is very specific for Meerkat is the layout of the telescope. It has a 70% of the antenna in the core. These give you very excellent sensitivity to extended source. And this is very important for galactic study. Oops, no, okay. This is how Meerkat is operating. There are these legacy survey that you see on the right, but there are also some Sarao legacy survey, the observatory legacy survey. And one is the Galactic Center region. That is already available to the community. The very famous picture that was shown, and I will show you more in details. There is the Meerkat Galaxy Cluster Legacy Survey, again, is already available for the community. The Magellanic Cloud, the galactic plane, is at the moment on science exploration. Meerkat has already open call for the community, so it's possible to apply to get some time. There is the new project called Meerkat Plus, where also ENAF is involved, is Sarao, Max Planck, and Italian ENAF project. The idea is to extend the Meerkat, adding 16 SK type antennas. These will produce for Meerkat higher resolution in L band, going from 8 arc second to 3.4 second, And when you have a higher number of baseline, because you put more antenna, you just don't have just sensitivity, but you have also the capability to get improved calibration, a better image fidelity. The project is already started, but it is going very a little bit slowly because the international problems, you know, also problem with the pandemic and so on. Anyway, is started. The antenna are under construction, and the project will run until Meerkat will be integrated into the SKA. So Isabella tell you it's going to be about around 2029. But this, as I put just a red arrow because it will depend on the international context. Inside this project, there is 50% that goes GTO time that go through the consortium. And this is the three kind of survey the consortium we will carry out. The rest is 90% of this time will go to the community. So again, more opportunity for the community to get this kind of data. Sorry, it's very, I don't know. Okay, galactic radio astronomy. We can summarize the final goal of radio galactic astronomy is to try to understand the cycle of matter in our galaxy and between these components. You know, stars form from molecular clouds, and then in some there is a feedback for the stars to the ISM through supernova explosion, planetary nebula, and stellar winds. So we really want to understand the types of such cycle of matter, and actually radio can provide you with a lot of diagnostics that you can use to understand this. We can track ionized gas by radio recombination line and thermal continuum. We can study all different kind of phenomena in our stars, look at thermal and non-thermal radiation. And the final goal is to use these results out and play to understand how other galaxy works. Okay, so you can understand with the unique capability, the SKA we have, the big impact on the galactic science. A lot of information, we can get a lot of information in the topics of a massive stars formation, because you have a complete census of H2 regions, for example, but also to study interaction between giant H2 region with the interstellar medium to look for trigger star formation. We can get new numbers for star populations, detecting new supernova remnant planetary nebula that then will provide us with a lot of constraint on evolutionary models. And we can have a lot of information, radio stars, and again, serendipitous discoveries that will be very, very important for the SKA. So why we want to do galactic plane survey with SKA precursor, if SKA is going to do that? First of all, I mean, we can summarize in two different aims. The first one is scientific, as I say, to anticipate what SKA can do in the galactic studies, but also because we want to face a lot of technical problems that we have when you do radio observation in the galactic plane. We have a lot of diffuse emission, so we have to find the best algorithm to select to extract compact source. We have variability issue. So it's very important to get those observations, to get clue on this kind of technical problem, hopefully to in some sense to overcome them. So in the context of the EMU survey, I show you this is one of the legacy survey that ASCAP is going to start next month. I mean, the main aim of EMU is to understand how galaxy forms. They plan to look to discover 40 millions of galaxies just because the sensitivity 10 microjansky and the resolution 10 arc seconds. But again, if you look at those numbers, we will see that MU will provide a very, very complete galactic plane catalog of galactic source. And actually, they will bring some bridge between the actual radio survey on the galactic plane. They are all very concentrated, very small patch of the sky with high sensitivity, or very broad patch of the sky with very, very low sensitivity and angular resolution. Okay, this is the first glimpse of a galactic plane. As I say, this is data from ASCAP in the early phase of ASCAP. It's done just with 50 antennas out of 36 antenna. And we already have a catalog of this area, big 6 by 6 degrees of the galactic plane centered at 343 longitude. And we have more than 4,000 compact sources already found them. And this first result highlight the capability to map with ASCAP the galactic plane, and at the same time to recover extended source and have the very good resolution to get all the details of a complex source. This is called a family album for Scorpio. You can see star-forming region with the massive young stellar object inside, another sun-forming region, and 2 supernova remnants. I'll just show you to give you an appetizer, what are the observation to answer to Giuseppe, the kind of observation you can get on ASCAP. This is a complex star formation region. And here you have 2 supernova remnants. Again, you can see most of the details of these sources. I will show you later what we can get when you have this kind of images. And as again, this is another part of the Scorpio field that you again can see 2 supernova remnants, a lot of filament. And this is in some sense a new discovery, because we know there are a lot of filaments around the center part of our galaxy, around the Sagittarius A. But now we are discovering this kind of magnetic filament also far from the galactic center. This is just to show you how many the impact of different stellar stars population. This is for H2 regions. In the Scorpio field, we have 96 new discovered detection H2 region. What is very important, we detect 99 sources that were supposed to be radio white. So the answer is, again, from Giuseppe, actually, with this kind of observation, we actually detect sources that are supposed to be radio white, while it was just problem related to sensitivity. And this is the same from planetary nebula. We had 48 planetary nebula falling in our field, and we detect 34 of them, 20 are completely new detection. This is also for the kinds of supernova remnants. We have we have 14 known supernova remnants and 5 candidates. We detect all of them. And again, when you get so good sensitive and detailed maps, you have also good flux sensitive estimation, because we can discriminate, disentangle between the real remnant and the source field that sometimes you cannot disentangle. And this is finally what happened when you put together information different wavelength. You see this as data superimposed. We have the blue is the radio, while you have the 8 micron and the 70 micron from Herschel. You'll see that you have the correspondence of dust and ionized gas in the case of star-forming region, while you expect to see very few dust when you look at supernova remnant. And this, you can see just looking at that, you can pick up supernova remnant that point out just in the blue. So this is the way how you just visually can spot some supernova candidate when you use a synergy between different bands. This is just some result for the other precursor, Meerkat. This was I was talking before. This is the galactic center images of done with Meerkat. Beside the Sagittarius A, the big Hercule region, you will see you can really appreciate the extended mission, but the very, very small details. Again, look at the many filaments you see around the center of our galaxy. There is another survey that is going on right now, the Galactic Plane. This is observatory survey, and this will be available for the community next year. It's done in L-band with the Meerkat, mostly the third and fourth quadrant. And just because it's a legacy survey, at the moment is managed by a consortium. This is to give you the difference between the same region looked with the VLA at low frequency, and on the right you'll see in the low right you see how details for this is a supernova called tornado, and if you look at the Meerkat data you understand what is tornado. It's you can really appreciate all the details. The standard product of such survey that again will be available next year, at the beginning of next year, as 3 degree times 3 degree tiles, and actually a data cube, because you have a different map within the map. So you have 12 maps for each frequency within the bandpass. And this is some results are preliminary, but as some result from this Galactic Plan survey. This is the catalog of extended diffuse source that you can see from this tile. At the first release, only 17 over 56 tiles were analyzed, almost 150 degrees square. But again, what is important, we found more than 1,000 sources. 22% correspond to galactic non-object, and 41 extragalactic, but 37 are completely unknown and unclassified. Just to give you a flavor of the unclassified source, you got a lot of different kind of morphology. This is some results on the planetary nebula of this survey. And what is important, again, we discovered in the radio more than 170 planetary nebula. And you see the orange one is the distribution of the new discovered planetary nebula. And again, the distribution peak around B of latitude 0 means that with radio, we are going to discover the very low latitude planetary nebula. So we are really increasing the population of such object. And this is my final slide. This is another discovery that we are doing from MIPS-GAL. We discovered these strange bubbles in the galactic plane. They're discovered at 24 microns, and actually they don't have a counterpart usually on the shorter wavelength. So only 30% of these 400 bubbles were identified. Mostly was those that have optical counterparts, and we are looking at them, and we are discovering in a galactic plane Meerkat survey, and actually we detect 158 of them. This is a very, very interesting, promising sample to look for evolved star, for example, in the galactic plane. My last slides I can leave here is outlook and conclusion, just to summarize when I need, and just to give you, I said, a very first update for the big launch that will be SKA.
Thanks to Grazia. There is time for some questions.
Thank you, Grazia. Very, very beautiful results. I wonder for all the unknown sources, if the multi-frequency campaign is already planned, especially for the optical classification.
No, there are no plans. We really understand that we need this. So something that perhaps we can discuss this afternoon, how organize some synergy between radio and other part of the electromagnetic spectrum. But again, it's a very good point. I mean, we really have to sit down, discuss, and organize this.
Okay, thank you.
Grazie, very interesting results. I have a curiosity. I was wondering whether you already have the feeling that you are tracing the structure beyond the galactic center. I mean, just on the other side that we cannot reach yet with this big view as you are doing with the radio, in particular in the distribution of the gas and also the sources beyond.
Yes, we hope to do that. But again, in this, in what we are doing, we are just looking at the source. Something else that we can do is trace ISM. So you need to look at different kind of, as I say, survey. For example, when you're doing spectral line, because in spectral line, radio recombination line, you can also get some clue on the velocity of the gas. So actually, you can really trust have a three-dimensional, I say, distribution of the material. But I was just talk on continuum. But this is it's a good point, an SKA, and perhaps next survey that we can do with Meerkat on ASCAP. And yeah, let's talk about this.
We can thank again. Grazie. I move on the next talk. Innocenza Busa will speak about the case of LSST-radio synergy, mapping the Galactic Cosmic Rays sources.
Thanks, Ilaria. Thanks, Grazia, Isabella, and the SOC to give me this opportunity. Yes, I will talk about a particular case of radio synergy with the LSST that is mapping the Galactic Cosmic Ray sources. The aim of the talk is to present the scientific preparatory work we are doing in support of the in-kind directable software contribution we will provide to the Milky Way Science Collaboration in 2026 and discuss how the scientific goals will be enabled and enhanced by combining the Rubin data with the radio observations. Briefly, I will introduce the new highlights on the origin of galactic cosmic rays. Then I will describe charge exchange emission and the theoretical expectation that lead us to use this emission to detect the new galactic cosmic ray sources. And finally, I will talk of the current radio synergy we are working on and about the future synergy perspective. We have several modules. Cosmic rays are charged particles accelerated at relativistic speeds that, according to the mainstream interpretation of the so-called supernova remnant paradigms, are accelerated at the supernova remnant shock by first order Fermi mechanism. But some recent observations challenge this commonly accepted scenario. In particular, a sharp break, a change on the spectral index of high energy electrons has been observed and can be interpreted by a stochastic model of different sources. This steepness of higher steepness of the electron spectrum with respect to the proton spectrum seems to indicate that the injection has to be different for electron protons, and this means could mean different accelerator source. Furthermore, multi-TeV electrons have been observed in the spectrum at Earth, and due to the short time of energy loss of these electrons, they should have been formed at a distance less than 100 parsec, where no supernova remnant has been observed. This information led us to strongly think that a new important source of cosmic rays has to be found besides supernova remnants in the local galaxy, which could be the possible candidates, of course, the gamma ray source like pulsar wind nebula, binary stars, superbubble, star formation region, and flare stars, but also strong wind outburst stars like Wolf-Rayet and luminous blue variable stars. A clue comes from the overabundance of the neon 22 observed in the cosmic ray spectrum. And because this neon 22 is just synthesized in the core of these high mass stars. In order to disentangle source from candidates, we have in mind to measure charge exchange in the region, in the clouds, around this candidate of cosmic rays. We will see in the next slide that this measure, this detection of charge exchange, will give an alert of the presence of cosmic ray, and so of the possibility to have a candidate, a source of cosmic ray. But the multi-wavelength synergies with all of these other wavelengths will be fundamental in confirming the cosmic ray source, so transforming the alert in discovery. What is charge exchange? It's just a collision between a fast ion and a steady neutral atom, in which an electron transfers from the atom to the ion, producing a fast neutral. Here we are dealing with the charge exchange from protons colliding with the neutral steady atoms, but we plan to extend the analysis also to heavier atoms. Charge exchange is observed in many supernova remnant filaments like the one in the figure on the left, and spectroscopically produce large and strong Balmer lines that can be reproduced by a narrow component you see in the center that is due to the recombination, radiative recombination, and a broad component that is due to charge exchange due to the post-shock high velocity protons colliding with the neutral pre-shock hydrogen atoms. We have theoretically derived which is the ratio of the number of photons emitted in the H alpha and H beta Balmer lines, and it is shown here on the left. When we compare this with the standard recombination fluorescence, we see that there is a strong difference, about twice. We have a line ratio about 4 for the charge exchange compared with the 2 for the combination. This led us to hypothesize to use this H alpha H beta ratio as a discriminator of charge exchange. That means discriminator of the presence of cosmic ray source. We have tested our method in the supernova remnant, known supernova remnant RCV86 on the right, and in the slits placed just on the filaments, we have analyzed the H alpha and the H beta profile, applying the profiles and fitting with the broad and narrow component, and we have compared the observed broad component ratio with our theoretical result. We see that the observed data are in the range of uncertainties of the theoretical curve, and this gives strength to the possibility to use this ratio in our analysis. When we look at the filaments in the red box, the Balmer-dominated filament in the red box, where we have found the charge exchange, and we compare with the radio map, we see that there is a spatial correlation between the two. While when we do the same overlapping in a radiative region, the green box, we see no emission both in the radio and in the charge exchange. Furthermore, because we know in LSST we will have photometry and not spectroscopy, we have tested how the photometric enhancement of the H alpha H beta ratio turn in photometric R minus G color index. The red box where there is the Balmer-dominated filaments has been on the right. We have the counts, and what you see that the enhancement, the spectroscopic enhancement, translate in a evident R minus G color index enhancements. Both these two things, RMNG and radio mapping, led us to begin a collaboration to implement a tool for mapping cosmic ray source using both to the wavelength. So we are working on the possibility of map the charge exchange in the optical, the synchrotron, analyzing the radio map, obtaining the spectral index that gives the synchrotron emission mapping, and using the cross match for improving the tool. We are working, the step that allow the charge exchange mapping include some steps that at which we are working on inside the Rubin Science platform, and using the DP02 simulated images, in order taking in mind that we have to include this tool in the LSST pipelines. The analysis has begun on the EMU survey of which has talked Grazia before, obtained by the ASCAP SKA Pathfinder in a 115 square degree the Scorpio field at angular resolution about 10 arcseconds at the frequency of about 1 gigahertz, and an example of a tile of the Scorpio field is shown on the right. The same field has been obtained in the optical range by the Busa plus VLT survey telescope survey, and here is a mosaic of the CCD shown on the right that has an angular resolution of about 1 arcsecond, and look in filter H alpha, U, G, R, and I. This is in particular the selection of 2 known supernova remnants in the field, and this is the field around just this known cosmic ray source we are beginning to work to implement and test the tool. We have begun this collaboration, and we are studying in the fast the pixel level mapping of the charge exchange, and at the same time in the radio map the pixel level mapping of synchrotron, and we will use cross-matching to obtain morphologic but also energetic constraints that can be used to improve the tool. We plan to apply the definitive tool to candidates besides the known supernova remnants. In the Mercat Galactic Plane survey that Grazia told will be maybe available next year, hoping that in the meantime the collaboration has enlarged the synergy, also including the synergy for extraction of extended galactic source and the classification of the candidates that will be necessary for our analysis. Fulfilled these steps, we will be ready for the next exciting years, where we will have the Rubin telescope with the LSST survey, and in most probably in 2027 the Mercat Plus Legacy survey, and 2029 maybe SKA, all with the subarcosecond angular resolution that will shed light on the original cosmic ray and much more. Thanks.
We have time only for one short questions. No? Okay, let's thank Innocenza for her talks, and we can go to the lunch in the auditorium. Yes?